Welcome to this explainer. You know, if you've ever felt like chemistry is just a random collection of invisible forces, you are absolutely in the right place. Today, we're going to demystify the abstract theories of chemical bonding. We'll show you exactly how the universe connects at the microscopic level. And honestly, mastering this invisible architecture, it's literally the ultimate cheat code, not just for your upcoming competitive exams, but for your entire future career.
Okay, let's dive right into this by picturing atoms as, well, restless Lego blocks. If you look around you right now, you're almost never going to find atoms just floating around entirely on their own. They hate being isolated. Instead, they link up in endless, crazy combinations to form the immense variety of materials we see, touch, and use every single day. Chemical bonding is essentially that invisible glue holding all these atomic Lego pieces together to create reality as we know it.
So, here is our roadmap for today. We're going to hit 5 key areas: the quest for stability, bonding in daily life, the core chemical bonds, geometry and special forces, and finally, wrap up with exactly why chemical bonding matters. Let's kick things off with Section 1, the quest for stability. Exactly why do atoms go through the effort of bonding in the first place? Well, in the atomic world, most atoms naturally have incomplete outer layers of electrons. This makes them highly reactive and, frankly, pretty restless. So the crucial takeaway here is that atoms will do whatever it takes, share, give, or take electrons from their neighbors, just to achieve a calm, stable equilibrium with a completely full outer shell. It's this universal craving for stability that drives literally all chemical reactions. And this drive for stability brilliantly illustrates why bonds are so vital. Think about graphite, the soft lead in your pencil, and compare it to a diamond, an unbreakable cutting tool. Both of these are made entirely of pure carbon. It's wild. The drastic difference in their physical properties doesn't come down to what atoms are present, but exactly how their chemical bonds are architected. Right, let's zoom out a bit for Section 2, bonding in daily life. Let's explore the invisible bonds around us that hold your entire day together. Invisible forces are literally at work everywhere you look. The water you drink, it relies on covalent and hydrogen bonds to stay liquid at room temperature. That smartphone in your hand uses covalent bonds in its silicon chips. The heavy steel chassis of a school bus relies on metallic bonds for its immense strength. Even the DNA unzipping in your cells uses hydrogen bonds, and everyday soap uses hydrophilic and hydrophobic properties to wash away grease. Basically, everything relies on a very specific type of atomic partnership to actually function. Moving right along to Section 3, the core chemical bonds. We're going to look at the 3 main mechanisms atoms use to lock themselves together. Our first mechanism is ionic bonding. This happens when one atom completely transfers one or more electrons to another atom. By doing this, one becomes positive and the other becomes negative. This creates oppositely charged ions, leading to a powerful, almost magnetic-like attraction between them. To see this in action, just think about what happens after a tough summer sports game. You're sweating heavily, losing essential salts like potassium chloride and sodium chloride. When you chug an electrolyte sports drink, the ionic bonds of those salts literally break apart in the water of your digestive system. They release these vital, free-floating ions that your muscles and nerves desperately need to keep functioning and stave off cramping. Our second core mechanism is covalent bonding. So instead of completely transferring an electron, covalent bonds are all about sharing. 2 non-metal atoms will share pairs of electrons really tightly between them so they can both achieve those highly desired, stable outer shells. And you interact with covalent bonds constantly. The plastic casing of your laptop, the Tupperware holding your lunch, these are made of polymers like polyethylene. Because these materials feature long chains of carbon and hydrogen atoms sharing electrons incredibly tightly within the molecules, those electrons aren't flowing freely. And that makes these plastics absolutely excellent thermal and electrical insulators. Our third core bond is metallic bonding. Here, you have a lattice of positive metal ions sitting surrounded by what chemists call a sea of delocalized electrons. In this setup, the outer electrons just aren't anchored to any single atom at all, because the sea of outer electrons can flow completely freely, like what you find in the copper wiring of a phone charger or an EV cable. Metals become absolutely exceptional conductors of electricity. It's a pretty brilliant system. Okay, Section 4, geometry and special forces. Beyond the basic connections, we really need to understand the complex shapes that dictate how materials behave.
Let me pose a practical question. Why does solid ice float in a cold liquid drink? Have you ever thought about that? Normally, when substances freeze and turn solid, they get denser and they sink in their own liquid form. So what invisible force is keeping your ice cubes miraculously afloat?
The answer is hydrogen bonding. It's a special type of strong dipole-dipole attraction between molecules. As water cools down to 0 degrees Celsius, these hydrogen bonds force the H2O molecules into a rigid open hexagonal lattice. This specific geometry actually makes the ice less dense than liquid water. It's a totally critical phenomenon. It causes ice to float, which famously protects aquatic biodiversity by keeping winter lakes from freezing completely solid.
And speaking of geometry, we have to talk about VSEPR theory. That's valence shell electron pair repulsion. This theory states that electron pairs around a central atom will repel each other, and that dictates a molecule's exact 3D geometry. This perfectly explains how medicines interact with your body. When you take a painkiller, that drug molecule acts just like a physical key that has to have the correct spatial geometry to bind perfectly to specific pain receptors in your nervous system. If the geometry is off, the key just won't turn.
Another totally fascinating geometric concept is hybridization. This is essentially nature mixing standard atomic orbitals to form superstructures. For example, carbon fiber relies on sp2 hybridization. This specific mixing creates flat, incredibly strong networks of bonds. It gives aerospace engineers and bicycle manufacturers a material that is a fraction of the weight of steel, but possesses immensely superior strength.
Let's zoom all the way out for our final section, Section 5, Why Chemical Bonding Matters, and specifically, how it impacts your future.
Look, if you're aiming to conquer highly competitive exams like IIT JEE, NEET, BITSAT, or NEST, chemical bonding is your absolute architectural blueprint for both organic and inorganic chemistry. These entrance exams aren't just going to ask you for rote definitions. No way. They will test your ability to apply these concepts, predicting molecular geometries using VSEPR, comparing the thermal stability of ionic lattices, or analyzing dipole moments. A rock-solid understanding allows you to decode complex reaction mechanisms intuitively, meaning you can solve those high-weightage conceptual numericals with real speed and accuracy. But beyond securing a top rank, this knowledge is literally your primary tool for the future. Whether you end up as a materials scientist developing next-generation semiconductor wafers, an environmental engineer designing sustainable polymers for the circular economy, or maybe a biotechnologist mapping hydrogen bonds and DNA for medical breakthroughs. These concepts are the very foundation of Industry 4.0. So, the next time you look around, remember that everything you see, touch, and use is really just a collection of atomic Lego blocks held together by invisible forces. Understanding how the universe connects at the atomic level empowers you to actually manipulate matter. So the question I want to leave you with today is this: how will you use your understanding of these invisible atomic connections to build tomorrow's innovative materials and shape the future of our society?